Now we're going to talk about the application of plane strain theory, and what we're going to talk about is what is termed as a thin-walled pressure vessel. Now, thin-wall pressure vessel theory is a common method used for analyzing boilers and tanks. And the reason that we do this is because boilers and tanks are subjected to very complex loading that we can simplify by using plane stress theory. The first thing that we need to do is we have to define what a thin-walled pressure vessel is. And the way that we define that is based on the inner radius of anything, because obviously it's going to have some kind of radius somewhere. So the inner radius we term as R over the wall thickness. Typically, these things have a constant wall thickness to keep stress concentrations out. But any time that that ratio is greater than or equal to 10, we consider it a thin-walled pressure vessel. Why? Once again, where does that number come from? Why 10? Well, let's look at when we have a radius over thickness ratio equal to 10. At this point, this is the level where we've decided the cutoff is at R over T equals 10, stresses are 4% below theoretical. Theoretical. What does that mean? Well, that means if we find out the stress is 100,000 psi, by equation, the stress is really 96,000 psi. And it becomes much more inaccurate below 10. Now, as we go above 10, it becomes more and more accurate. So we get closer and closer to that real number from our equations. So if the vessel is thin, we can assume that the stresses are uniform and constant. And then and because they're uniform and constant, they're basically acting in one plane, and we can apply this plane stress theory to. Okay, so as we start looking into these pressure vessels, we need to talk about pressure just a little bit, and I know this is something that'll come up when you take a fluids class, but everything that we're going to be dealing with is what's going to be called in gauge pressure. And so gauge pressure means that we're not looking at atmospheric pressure. Everything's in relation to atmospheric pressure. So if I sit here and look at this and I've got, my pen stopped working. If I've got the outside of the tank, I'm pushing on it with the atmospheric pressure. On the inside of the tank, I have it pushing back with some atmospheric pressure plus whatever pressure in the tank is. Gauge pressure, and it's called that because you're reading it off the gauges, just goes, well, the atmospheric pressures are canceling each other out. So I'm just looking at how much above atmospheric pressure the tank is. And so that's typically what we're going to be doing with all of these. Is the distinction super important for this class? Not really, but I just wanted to let you know with what's going on. So pressure vessels, we have two types that we end up dealing with. We have a cylindrical pressure vessel, and so it's just what it sounds like. It's a cylinder. And we have a spherical pressure vessel. So we have a sphere. And the reason that we have that is we have different kinds of stresses in those. So let's take a look at our first one. So this would be our thin-walled pressure vessel that's a cylinder. And you'll see I have listed there, we have two types of stresses. And the stresses correspond with our principal stresses on our Mohr circle. In fact, the principal stresses have to deal with a three-dimensional Mohr circle, which we haven't gone over, but we're not going to worry about that too much. And so you have two different stresses that you're worrying about. You have the stress because the pressure is trying to blow this end cap off. And so you have a stress there that we call the longitudinal stress because it's on the longitudinal axis. The other stress that we have is the stress as it's trying to rip itself apart along the diameter, and that's called the hoop stress. So where does that hoop stress, where does that word come from? It actually comes from back when they were making barrels, and they first figured this out. Let me just quickly draw a horrible, horrible whiskey barrel there. And so they'd have these iron bands on it to hold everything together, and they're called hoops. And it's the whole thing came down to the stress in those hoops, and that's why hoop stress. But anyway, so how do we figure this stuff out? So let's look at hoop stress first, and we're going to draw a free body diagram. And so if I split my cylinder right along the axis and I start looking at, oh, what do I have? I've got some stress that's over the area that's pushing inward, that's trying to hold the material together to keep it from being ripped apart. And then I have the pressure pushing outward, and that pressure is trying to rip everything apart. So if we do a sum of the forces in the x direction, and we'll say, and actually let's be consistent with the picture, it's the sum of the forces in the z direction, and we'll say that this way, that in is positive, they have to equal 0. So what I have is I have that stress that's pushing outward, so that equals minus 2. Now to get the force, it's going to be the stress 1 times dA, the area, and so we'll end up summing over all that area. And then we have the pressure pushing inward. We have the pressure pushing down on it. So we're going to add to that the pressure. Now, the pressure, because this is a complex loading, if I actually looked at the side here, because pressure always acts at 90 degrees, the pressure on this is actually going to look something like this. That's crazy. That's crazy complex. We got a lot of stuff going on. So what we do is we simplify it, and we estimate it by going, okay, well, here is my hoop. I'm going to take that projection, and I'm just going to calculate out the pressure on that projection. And so the crazy thing about this is that's actually a really good estimate of what's going on. The theory and reality with this one line up fairly well. Okay, so let's go over here. So we got the sum of the forces equal to 0. And I've got that pressure. So pressure. Now I need that area. So what's that area going to be? Well, that area is going to be, here's our radius of our pressure vessel. And so it's 2 radius times the width. And so in this case, the width is dx. We're going to use that, our differential dx there, because we'll be able to cancel it out. Okay, and so then on the other side, we've got 2 times that stress 1. And then we're looking at, okay, well, it's over the area they're dealing with. And so that area is the thickness of our shell times dx. And there we go. I'm going to be able to move it to the side. I'm going to be able to divide through. I'm going to be able to get rid of that delta x. And what I'm going to be left with is my hoop stress is going to be the pressure times the radius over the thickness. And so that is how I would calculate out my hoop stress. Now, longitudinal stress, let's take a look at that. For some reason, my slides are not indexing. And now let's do the same thing. So as I look at my horizontal stress, I've got all that pressure pushing along the edge that's trying to blow the top off, and I've got the stress that's holding it together, that's trying to keep everything from blowing up. So sum of the forces in the x direction is going to be 0. So what do I have pushing out? Well, I have the pressure pushing outward. I'm actually using the terms outward and inward. If we're going to take this to be positive, we've actually got the stress going outward. So let's do that first. So the stress, what's the stress going to be? Stress 2. Now we got to multiply it by the area to turn it into the force. So to do that, I need to know the diameter and then the thickness, because if I take the circumference and then I multiply by the thickness, I'll have the area. So what is the circumference? 2 pi r, and the thickness is t. So that gives me the area over which this stress is acting. And then coming the other way, I have the pressure. So the pressure is acting upon the inside circle, pi r squared. And so if I look at the longitudinal stress and I calculate this out, stress 2 is going to be PR over 2T. And so that's our longitudinal stress. And notice that stress 1 is twice stress 2. So what does that tell me? Well, it tells me with a pressure vessel like this, the hoop stress is more important because that is where we're going to fail, is in the hoop direction and not the longitudinal direction, unless there's some kind of imperfection or whatnot in the longitudinal direction. If everything's perfect, the higher stress is going to be the hoop stress, and so the failure is going to be a hoop stress failure.